Good morning, Ignite students. Here we go. We've got another day. We're going to finish up the last two little bits of volcanic formation. Then we're going to talk about the other stuff. And then we're going to wrap things up and head in and talk about when the test is going to open up. All right, let's get started. Review to scale. Remember, ocean level here. This is Mauna Loa profile where distance and height are actually to scale. And so you've got this huge mass under the sea. Shield volcanoes are massive. Composite cones are what you think of when you hear volcano. And then a cinder cone is a one and done. Little guys over, done with. All right. That was last week. Good profile, good reminders. Here we go. So these are the three big types of volcanoes. What else could there be? Well, let's start with caldera. Okay, caldera is a really cool thing. It's a depression. It's a hole in the top of the volcano. This happens often. When we looked at Mauna Loa, there was a small water lake in there. And now that it's erupted since December, that lake is obviously gone. So, how does the top fall in? Okay, how does the top fall in? Two ways. Either it collapses, the top collapses after a huge eruption. Think like Mount St. Helens, where you erupt and remove all the rock from the side, and then there's this big cavity left, kind of like that. Or two, on a big shield volcano, after the magma dome, or not the magma dome, the magma chamber is drained. It's empty. There's nothing supporting it anymore. All right. So just a good picture of a clean caldera. All right, let's get rid of that. Let's get rid of that. Here you go. There's a nice one. All right. This is in Ecuador. This is the peak of a volcano. It's kind of wild. All right. Here we go. We're going to run through a few of these. Let's shrink this down for a second. Crater Lake. Oh, Crater Lake in Oregon. Actually, not crater. I got to speak better. On the video, it's not coming out right. Crater Lake is this thing. It's not really from a meteor crater. It's because there's a volcanic chamber that's missing support underneath. This is Wizard Island in the middle of Crater Lake. People get to name things. They're kind of weird. All right. This is just another one here. And you've got some islands in it that continue to form. Big spots. Shield volcano craters are different than the Crater Lake ones because they're sinking slowly after the magma chamber drains. Okay? So, the caldera at the summit of Mauna Loa. Okay, another shield volcano. All right. Lake Toba here. Okay, resurgent calderas, meaning that it keeps coming back. There can be an eruption. There can be all sorts of other stuff. It over and over and over. Okay, we got forest fires over here. But there is a collapse of a big magma chamber going on. All right, Yellowstone, back to here. We gotta move. All right. What else could there be? So if there's three types of volcanoes, there's shield, there's cone, and there's cinder, right? And then there's caldera. There are also necks and pipes. Necks and pipes are the other two volcanoes type things that are left over. So, a neck. This is a before and an after. So there is a huge giant volcano 20 million years ago. The inside of this volcano, it cools and it goes dormant. Well, that is magma and lava. That is igneous rock in there. It's volcanic rock. This out here may have been sedimentary, may have been metamorphic, could have been something else. But as it erodes, the igneous rock erodes less, and you're left with this neck sticking up like that. This is shiprock. Okay, a couple images of shiprock. This is New Mexico Tech University. There is shiprock. There is shiprock. All right. So these are the neck. You might hear the term neck or pipe. The pipe is sometimes what it's called that connects the chamber, the magma chamber, up to the vent and the opening. And so your neck and a pipe kind of interchangeable. There's a difference. But what's left over is the neck after the erosion. Okay? Let's see. Wait, I think there's one more. Oh, here's another example. This isn't really an interesting one. This is not above ground. Sorry, I had to check my notes here. Kimberlite is a type of rock. There's an area in South Africa that the pipe goes all the way down deep enough to a spot where diamonds are being formed. So as the volcano erupts, these rocks bring diamonds up to the surface with it. Harden, erode, and you get this other weathering alongside this pipe. All right. Okay. Lava flows. Lava flows are huge, vast fields of lava. So, get 3 volcano types. We've got calderas, the hole in the peak. We've got necks and pipes. Necks are above and then it's weathered away. You've got lava fields. All of these are volcanic. There was an active volcano. Magma reached the surface. Features. And we need to put a big dividing line right here between what we've talked about last week, the 3 volcano types, and then caldera, necks and pipes, and lava fields, and what we're about to talk about. Because what we're about to talk about happens very differently. So lava fields, by the way, just slow, there's no big eruption. It's just slow oozing out of a fissure. Okay. Here you go. Plutons. Okay. Most magma cools deep in the earth before it ever comes up. And it hardens into an igneous rock in the earth. So what results is plutons, is different ways for that igneous rock that's below the surface to become visible to us. There was no eruption. There was no major volcano. No flowing magma ever turned into lava. There was no lava. That was all before. Now it's after. All right. Plutons are these different features. Okay. So there are sills, laccoliths, dikes, stocks, batholiths. Sorry. So these are all types of plutons. All of these are plutons. And instead of a pluton, how about an igneous intrusion? That's really what it's called. That's the geology word. igneous intrusion, because it's going to be igneous rock and it's intruding, it's going into layers of other rock, whether that's sedimentary rock or metamorphic rock, more likely sedimentary. These happen not deep in earth, but they happen very shallow and vary ranges depending on which type. Sorry about that. Here we go. A sill right here. Magma is injected into sedimentary rock, between layers of sedimentary rock, and it's usually parallel with the layers of the sedimentary rock. All right. And then later, something happens and that region is exposed. All right. So igneous intrusion, we talked about that. There's laccolith. Do we get rid of sills? Well, this is really a sill. Sill is the first type of this. Where did it go? So you've got all layer after layer after layer of normal sedimentary rock, and then you can get a layer of igneous rock injected in between there. And it cools and solidifies inside Earth. And then years and years later, weathering exposes it. That's what a sill is. All right. Now, a laccolith. Well, let's go back to this big picture. A laccolith is not a sill. A laccolith is magma intruded between sedimentary layers. Sounds the same. Near the surface. But the magma is more viscous. Remember, viscous means syrupy. It's thicker. It doesn't flow and spread out. It piles up and makes this dome shape in the layers, which lifts the layers above it. So as this hot magma flows up and it forms in here, this stuff is so thick, it doesn't spread out, it pushes up. That's the big difference between the sill and the laccolith. Sill would be thin lava, it's going to ooze in between the layers, and a laccolith, big, thick, gloppy stuff, is going to push up the sedimentary rock that's above it. Let's see the images. There it is. And I've got that was it. Yeah. So that is, you put, after it's pushed up, again, you wait and erosion leaves, it will erode down to that level. All right. So what's a dike? A dike is magma that's injected into a fracture. There's already a cut, crack, hole, crevice in the rock formation, and magma just takes that easy path right on up. This is an interesting one because you've got all these layers of sedimentary rock, and the magma just said whoop. And maybe if the crack ended, it would start oozing out sideways and become a sill or maybe a laccolith. But this is the magma filling in that crack in the fissure so it fills in the dike. And all right. It's Mount Whitney. That's Sierra Nevada. That's in a minute. Big one. Batholith. Batholith is big. Batholith is huge. It's the largest type of igneous intrusion, or Pluton. Remember, igneous intrusion and Pluton are the same thing. And Pluton describes all these things: the sills, the laccoliths, the dikes, the batholith. They are magma formations that cool off and solidify in the earth, and then later they're exposed. To be a batholith, you have to have a surface area of over 100 square kilometers. So 10 kilometers by 10 kilometers is bare minimum. Big structures, all right? So this stock is a batholith, just a little smaller. Mount Whitney is part of the Sierra Nevadas. It's part of a huge, huge batholith. This is a good picture, but it's out of focus. Like there's no context for the scale of this. Is 100 kilometers, but the Sierra Nevada batholith is this huge area of upheaval where there is igneous rock and this huge magma chamber that cooled off, and then the surrounding land was eroded away. All right. There you go. Dividing line. Above, if it reaches the surface as liquid magma and then lava, you've got shield volcanoes, cones, cinder cones, and the other type of cone, composite cone, which is a stratovolcano, right? And then you've got caldera, necks and pipes. Those are the things where magma reaches the surface. Below the surface, igneous intrusions or Plutons harden and solidify below the surface. Those are sills, laccoliths, dikes, and batholiths. Maybe a stock is a small batholith. That's it. That's what all this is. So that's the over and the under. Where does all this magma come from? Like, really, where does it come from? Because other than the core, most of the interior of the earth is pretty solid. There's some solid stuff. There's solid rock going on. All right. Crust and the mantle are mostly solid. So magma comes around when essentially solid rock partially melts. That's where magma comes from. Okay? The most obvious way is we're going to increase the temperature. We're going to raise the temperature a little bit. All right. Here's the heat. This is the geothermal gradient. The what? This says that as you dig deeper, the temperature goes up. This is temperature in degrees Celsius. Temperature goes up in this straight region right here. In this upper region, it's 20 or 30 degrees per kilometer in the upper crust. Okay? So that you get to a temperature of 14 to 1600 degrees out here at 100 kilometers. That's not quite the melting temperature of any rock that we're talking about. So how do they melt? There's two other big factors: pressure, water. Okay, well, first of all, let's stick with heat, because heat, pressure, water are the three things. So heat goes up, heat goes up, heat goes up, yes. Well, something down here can bubble up and rise moving through here. So it would rise up through the other, and as it's melted, it's able to move and flow through the rigid parts. Pressure. As you go down, pressure increases. But if the pressure increases, you actually, instead of melting at 1500 degrees, now you're going to melt at 1600, 1700 degrees as the pressure increases. It actually makes it harder. So what you do is you get something that's very hot and kind of solid here. If it gets caught up in a bigger piece moving, even though it's solid, as it moves up, it's not going to cool off very fast. And as you move up, you decrease the pressure. And decreasing the pressure lowers the melting temperature, which then allows it to melt. So it's interesting. It's that because it's under pressure, it stays solid longer and gets super hot solid. And then if it happens to move up where the pressure is lower, it'll quickly melt because it's going to keep that temperature. Third thing, water. There's no water in rock is not immediately steam because steam is down here at 100 degrees. Okay. Water in rock, if even just a small increase in rock, water decreases the melting temperature. So if there's the right chemical elements in there, the melting temperature of these things goes down. So heat, pressure, and water are the three main things that determine what is liquid magma and where the magma comes from. All right. I'm actually going to end on a bit of a question today. All right. This is Devil's Tower, okay? Very cool. The Black Hills. Okay. This is collimated rock, okay? It's very interesting, very cool formations that happen. But how did this happen? Okay. Formation, this is National Park Service, by the way. Geologists agree Devil's Tower began as magma, molten rock buried beneath the Earth's surface. What they don't agree upon is how it cooled and formed the tower. All right. Simplest explanation right here. Simplest explanation. It's a stock. A small, so not a batholith, but a stock. So this was all magma. See, look, land surface is up here at this green line. Sediment, 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 and then this magma comes up and makes this bubble like this. And then it solidifies. And then erosion, 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 and you're left with Devil's Tower. That's theory 1. Theory 2 is the laccolith theory. Land, sediment, and as you inject the thick, remember a laccolith was thicker, as you inject it, it bulges this up slightly, and then erosion, 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 erosion leaves Devil's Tower. Another idea is a volcanic plug. Possible that you get you got a small volcano here, right? And it erodes. The biggest thing, let's get down here. Let's get here. Concept of erosion is common to all of its modern formation theories. Ironically, the erosion which exposed the tower also erased the evidence. So it's really going to be hard to tell between these two or this one because everything you're looking for is eroded and gone. So there's Devil's Tower. Just a little curiosity for you. Go to the Black Hills. Okay. What's left? We have done plate tectonics. We have done volcanoes. We've done other magma formations. We're going to look at plate boundaries specifically to see how magma forms and interacts at the boundary. We're going to review. We're going to test. That's all going to open up and be kind of ready Thursday. Your review and the last section will be Thursday. So we can put the test to open maybe Monday. That's the plan right now. Guys, have a great day. We'll see you later.